Study guide for test 3, problem 7. If phi is a homomorphism from Z to Z8, defined with phi of n equals to n, find the kernel of phi and the image of phi. The kernel consists of all elements from the group whose image under the homomorphism is 0. And because of this definition, and because in Z8 the operation is, the numbers are reduced mod 8, we will have this equality 2n congruent to 0 mod 8. This means that 2n is divisible by 8, and this is true if and only if n is divisible by 4. That is, n mod 4 is 0. This means that n must be a multiple of 4, and this is the kernel. All integers that are multiples of 4. The image consists of the set of all images, of course, phi of n, when n is in Z. So 2n mod 8, when n is in Z. And here we'll get the numbers 0, 2, 4, and 6. And we cannot get 1, 3, 5, and 7 because they are odd. And here, when you reduce an even mod 8, the result is always even. So, this is a subgroup of Z8, the subgroup generated by 2. Problem 8. Let G be a group and A be an element from G. Define F sub A to be the map from G to G defined by F sub A of x equals A to the negative 1 x A for any x in G. Prove that F sub A is an automorphism of G. We have to prove that F sub A is group homomorphism, which means that for any x and y in G, we have this equality. This is easy to check. Just evaluate the left-hand side, you get A to the negative 1 xy A. Evaluate this, the right-hand side, you get A to the negative 1 xa, A to the negative 1 ya, and because in the middle A to the negative 1a are next to each other, their product is the unity E, so it disappears and you get the same result. So, F sub A is a group homomorphism, and it remains to prove that it is a bijection. A group homomorphism that is a bijection is a group isomorphism, and a group isomorphism from G to the same group G is called a group automorphism. So it remains to prove that Fa is onto G and Fa is onto 1. And we are done. To prove that Fa is onto G, we select any Z in G and show that it is the image, Z is the image of this element, A, Z, A to the negative 1 on the Fa. It's easy to check, just evaluate. You get A to the negative 1, AZ, A to the negative 1, A. A disappears, it remains only Z. Like this. So Fa is onto why FA is 1 to 1. If you have any x and y in G, and their images are equal on the FA, show that x and y are equal. Write this equality using the definition. You get a to the negative 1 x a equals a to the negative 1 y a. Cancellation law applies in any group. Cancelling a to the negative 1 to the left and a to the right, we get x equals y, which means that FA is 1 to 1. And we are done. Problem 9. Find all isomorphism classes of abelian groups of order 40. First, write the prime power factorization of 40. It is 2 cubed times 5. And then consider the different prime powers that appear. 5 is 5 to the first, so there is only 1. Because it is a prime, there is only one abelian group of order 5. This is Z5. It is cyclic. Then we hand out 2 cubed. Take the exponent and then write that 3 as a sum of non-negative integers in all possible ways. The order here to the right is not important, so you don't need to write 1 plus 2. Because 3 can be written only in 3 different ways as a sum of this kind, there are 3 isomorphism classes of abelian groups of order 2 cubed, and they are Z2 cubed, Z2 squared plus Z2, and Z2 plus Z2 plus Z2. So these numbers here to the right are the exponents that appear, the exponents of 2. So this is actually Z8, this group is Z4 plus Z2, and this is Z2 plus Z2 plus Z2. And then you combine each possibility for the 5 power, it is only 1, with each possibility for the 2 power. We have 3 possibilities here. This way we get this Z5 plus Z8, Z5 plus Z4 plus Z2, and Z5 plus Z2 plus Z2 plus Z2. There are 3 isomorphism classes of abelian groups of order 40. Problem 10. Let G be the group consisting of these 8 numbers on the multiplication mode 40. So it is given that these numbers form a group under this operation. We don't have to check this anymore. Determine the isomorphism class of this group. According to the fundamental theorem of finite abelian groups, this group must be isomorphic to one of these 3 abelian groups of order 8, because we know from the previous problem that there are 3 isomorphism classes of abelian groups of order 8. So this particular group G must be isomorphic to exactly one of these 3 groups, because any 2 of these 3 groups are not isomorphic. and G must be isomorphic to one of them. So, to exactly one of them. To see which one, we compute orders of elements of G. Because isomorphisms preserve orders of elements, this will allow us to eliminate some of the groups. 17 squared mod 40 is 9. 17 to the 4 mod 40 is 1. This means that the order of 17 in this group G is 4. And the order of 9 is 2, because 9 squared will be 17 to the 4th, which is 1. In the third group, Z2 plus Z2 plus Z2, all non-zero element has order 2. There is not an element of order 4. This shows that G cannot be isomorphic to the third group. Then we compute 39 squared. 39 is -1 mod 40, and 39 squared will be 1. This means that the order of 39 in G will be 2. And we have two elements in G that have order 2. Those are 9, the number 9 has order 2, and the number 39 has order 2. So G has at least two elements of order 2, and the first group G, Z8 is cyclic, and in a cyclic group we have exactly one subgroup of order 2. From the fundamental theorem, we know for each divisor of 8 there is exactly one subgroup of that order. 2 divides 8, so there will be exactly one subgroup of order 2, which means that in Z8 only the number 4 has order 2. So we have only one element of order 2 in Z8, while in G, the given group, G, we have at least two elements of order 2. So G cannot be isomorphic to Z8. And it remains only one possibility. So G must be isomorphic to the second group here, Z4 plus Z2. And we are done.